All right. Are we still expecting Lewis in person, or has he moved to the online list? Because I haven't seen him. Huh? All right. That was your breakfast? You're supposed to have, actual food. Coffee is not breakfast. Kids. All right, where to go? Fernando.
Where's the locker? I'm gonna just leave it there.
All right, we'll just go on without him. Okay. Good morning, everybody. Hello, Brian. Hello. Good morning. We got stuff to do. We got cool stuff to do. This is the beginning of the end, right?
What do you mean?
This is the last chapter of the book.
Really?
Yes, really. It actually is the final chapter of the text. This is the final chapter we'll be doing. Final section. We're gearing up for the end of the year. Okay? Final things. And as I pointed out last week, this last chapter will also be the subject matter for your final exam. Okay? So.
Like the exam we take is going to be about finding limits.
Well, this is the first section of the chapter. Yes.
So it's about
Chapter 11. Yeah. And the first section of chapter 11 is on finding limits. This is the basis of calculus. Right? We talked a little bit about that, right? All of PreCalc. What is the point of PreCalc? 1, mastery of your algebra techniques. 2, getting a preview of actual calculus stuff. This is the calculus stuff. Okay? All of the calculus rules work by being based around the concept of limits. So it's very important that you be able to read the notation. You've had to get used to function notation, right? F of x equals x plus 2, or whatever it is, right? Saying that there is a rule that says for every x I'm going to add 2 to it, and I'm going to give that rule a name. I'm going to call it f. Right? That was function notation. We're taking that one step further with limit notation. So now we might say, find the limit of the function. And here we have the function rule written out. You could also say limit of f of n. Right? Find the limit of the function as n approaches 5. Okay, so this is saying the limit as n approaches 5 of the rest of it. And we use that word approaches very deliberately here. That's the key difference. This is not the same as, hey, plug in 5 for n. It's not the same. It's almost the same. In fact, my next bullet point here, most of the time it will just work. You could just plug the value into the function, and it'd say, okay, it's exactly as you're used to plugging values, substituting values into a function. Okay? And when that happens, we say that, hey, the limit of the function as x approaches a equals the function of a. Right? Most of the time, for most functions, most values on the function, this is true. The limit anywhere, as I approach this value, well, you might as well just substitute it in. And this is part of what makes learning limits weird at first, because it doesn't seem like there's a point. Why all this extra hullabaloo, this extra notation, extra conceptual layers to do the exact same thing? Because it doesn't always work. I said most of the time, not all the time, right? Limits let us define when things get weird. The official definition for, hey, there's something wrong with this function. It's broken, but not everywhere. It works most places except for this value breaks the function. The official, way to calculate that is to use a limit. And in that case, the limit does not equal the function. We actually introduced this concept way back when we were studying rational functions. You guys remember rationals? Yeah, those guys, right? It looks like that, right? What happens when x equals 0? Stuff breaks, right? I can't put 0 into here. You can't divide by 0. You'll break things, okay? So how do we know that the function is broken? How do we define, hey, there's an issue here? We use this. We say the limit as x approaches 0 will not equal the function, right? And we get some form of a discontinuity. Okay. A lot of the times, these become very obvious when you look at the graph, right? Literally not continuous. As in, to draw this graph, I must stop drawing, lift my pencil up, move it somewhere else, and then continue. Discontinuous. That's the key here. This is the official way to define discontinuity. When is the graph not smooth? Well, actually, smooth is another layer up. We'll get there. Right. Now, the other key thing to remember, the limit only exists if both sides agree. We talked about approaching this value. Well, you can approach from a number of different angles. Just like now that we have two doors in the room, right? I can approach the room from two sides. I could come in through that door, or I could come in through this door. In this case, we have the left and the right, and they are exactly as they are described, the left and right sides of the graph. So the left side is coming in from the smaller values. Go from negative infinity forward. Okay. The right side approaches with greater values. Go from literally the right side of the graph towards what you're looking for. If both of those match up, then you have found your limit. If they don't match up, then there is no limit. It does not exist. So take a look again at our 1 over x. If I approach from the left, that means start at the left side of the graph, draw along the graph, and it goes down, 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 down towards negative infinity, right? If I start on the right side, go towards 0. It goes up, 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 up towards positive infinity, right? So the limit as x approaches 0 from the left side, 0 minus, numbers smaller than, right? Take 0 and subtract stuff. From that side, I get negative infinity. But if I approach from the right side, 0 plus, add some values to 0, so we're a little bit more than 0, I'm going to get positive infinity. So these two limits are not the same, which means the limit as x approaches 0, no plus, no minus, whole thing, equals does not exist. That is the official final answer to that question. What is the limit as x approaches 0 of 1 over x? Does not exist. The two sides don't meet up. Does that kind of make sense? Okay. Once again, it seems like it's either really obvious and it seems more work than necessary, but eventually we'll see things where it's not obvious, and this is the only way we can be clear and precise with, okay, what is actually happening, yes or no? Is it continuous? Does it add up? Right. So let's try our first example. We're going to find the limit using a table of this function. So we want to know the limit as x approaches -3 of our function x squared minus 9 all over x plus 3. And when you do that, when we say approach, we mean we get really close. It is not good enough to plug in, what's the next closest thing to -3? -2 is not close enough. You need -2.9. That's almost close, right? Something that would actually round to -3. 2.99, even closer. 2.999, that's what we're talking about. When we say get close, we mean get really close. Tenths, hundredths, thousandths. Okay? Which means that it's kind of going to be a pain to do by hand, wouldn't you agree? I do not want to try squaring 2.999. I don't know, do you want to? Like, that just sounds, they're going to come out with ugly decimals, right? Ugly decimals. Okay, sorry decimals, but you're less convenient than integers. So you can totally use graphing utilities to help you with this. Okay? That is to say, Desmos or TI-84 calculator. All right? Perfectly acceptable. So what I would do with this is I would go to Desmos. I'll type in my function. And Desmos automatically graphs it for you. And you can see, hey, we've got it, looks like a line. But is that a linear function? No, it's got this x squared up there. Don't you see that? Right? Clearly it can't be linear. It's actually a rational function. Right? It's got stuff divided by more stuff. Rational function. So if we think back to how rational functions, we could expect it. Okay, there's power of 2 up here, power 1 down there. Net result, overall, power 1. So yeah, it looks like a line, but it's not a line. We want to find the limit as x approaches -3. So the first thing we want to check is what happens if I plug in -3? Let's put that in the middle of our table. -3. Undefined. Oh, yeah, well, because look up here. -3 plus 3 is 0. I would be dividing by 0, right? Can't do that. But do you guys see a great big discontinuity on the graph? Like with the 1 over x graph? Place where it goes, right, shoots off and doesn't connect? No, you can't see it on here. So this is an instance where the table is really useful. The limit is clearly telling us, hey, there's something screwy going on. On the graph, it's undetectable, right? It's such a small discontinuity, we can't see it. In fact, we would find out that it's going to be a removable discontinuity. There's a hole in the graph at -3. So let's look. What's really close to -3, but is smaller than -3? So from the left, something more negative, that'd be -3.01. Right? Or we could go -3.1. And now we're saying, okay, -3.1 says -6.1. -3.01, I get -6.01. So this is a little more than 6. This is an even smaller bit more than 6. when I went even smaller bit more than -3, or less than -3. So it's looking like -6, wouldn't you say? Pretty close. Well, let's check the other side, just to be sure. So we want, this would be -2.9. 9. -2.9. 5.99 rounds to 6. Sorry, negative, right? So they seem to agree, don't they? And we could, of course, add more zeros and add more 9s and get closer and closer, right? But we're never going to be precisely on -6. Agreed? So does this function ever actually equal -6? No, but the limit tells us it gets close enough, right? Practically speaking, basically -6, right? That's what it means. Like, okay, come on. We can't even see, right? I can't zoom in here far enough to see the difference. There, notice here on the graph I have a solid dot. Desmos will show you an open dot when you are undefined. But you have to have your mouse right on top of it. You have to kind of know where it is already. Okay? The limits are a way for you to figure out, yes, this is a spot where it is undefined. We figured out last semester ways to analyze this function as is, right? To find out, oh, there should have been a hole there, right? So there's algebra techniques we could have used on this function. The limits is the more general case. This will work for any type of function where we can't immediately, just factor things out and find, yeah, there's got to be a hole there. Right? Am I making my case that it's at least plausibly useful in some cases? Let's try the next example. Here I have the graph, and yes, this is me taking a picture of the computer screen because I didn't want to, relying on the graph, I didn't want to try to redraw it myself and do it wrong. So here is our function. Find the limit as x approaches 1 of the function and f of 1. Okay, so it sounds a little funny. Totally reasonable. You look at this graph and be like, I don't see anything wrong with this graph. Can we agree on that? Look at it. Graph seems fine. Not broken anywhere. So we should expect f of 1, limit approaches 1. Those should give us the same thing, right? Let's find out. F of 1. 1 is here. To the function is right there. Looks like a -1. Okay, how about the limit? Well, to look at the limit on the graph, I need to go from the left-hand side, as I get closer and closer to, don't look at the graph itself, ignore that purple dot, look at the value when x gets to 1. So as I go along, as I get closer and closer to the orange line, I'm getting closer and closer to, down here, my laser pointer isn't small enough as I zoom in. It's approaching -1. Okay, so we got approaching -1 over here. How about on this side? From the right, we go down and it gets down here to that point, approaching -1 from that side. Clear? So the limit is also -1. Good, checks out, right? As we expected. It doesn't have to be hard. And again, it seems ridiculous. Like, what did we actually do here? We didn't accomplish anything. Of course, it was pretty obvious, wasn't it? Like, yeah. Again, we're practicing on the easy ones. Okay? You practice on the easy ones to confirm, okay, yeah, this is what it's supposed to look like. Because eventually we'll see ones where it doesn't meet up. You will not always get these nice, clean, smooth, curved, continuous functions out of everything. Right? Especially in the scientific and engineering realm, where your function comes from real-world data and measurements. You can't measure to 0.000000001. Right? Your instrument just isn't precise enough. Or in this case, we want to go close to 1, so 0.9999999. Right? You can measure to 0.99. You can measure to 1.01. So you have data points that exist, right here and right there. You're like, okay, but does that mean at precisely 1, how accurate can I get? What is the actual value there? See what I mean? You won't always have that level of accuracy, that confidence that it's precise. So you got to look at the trend. Oh, well, when I measure less than that, it was going this way. When I measured more than that, it was going that way. So I feel pretty confident that I can connect the dots there, right? But if this one was going this thing, and this one was doing that thing, you'd be like, what? Right? I don't know that I can connect those dots with a smooth line, right? The limits don't seem to match up. In fact, even worse, right? What if this was, over here? Like these come to this way, but then when I measured from this side, they went up this there. Oh gosh, right? This has happened to me before in college physics lab. That like you measure one thing, you expect a result, and then you turn the apparatus around, and it should still give you the same result, but something screwy, something goes wrong, you're like, oh crap, the data doesn't line up. What did we do wrong here, right? If you're a visual person, the graph of limits is usually pretty obvious. But let's make it more complicated. Here's a scenario where it's not immediately obvious what's going on. When I have compound functions, f of g of x, how do I find the limit there? Because now we've got an extra layer between us and seeing the answer. Notice a few things here. F has x squared, g has square root of x. Okay, so I've got these two operations that undo each other, right? But there's some limitations on allowable domains and ranges, right? Generally, I'm not supposed to put negative numbers in here. Right? We can't take the square root of negative numbers. We end up with complex answers. I really don't want to get into the complex plane here. So what's going to happen? Am I allowed to do that? That could throw things off right there. Just knowing that, I'm like, ooh, wait. Yeah, that's really going to do weird things with negative numbers there. That might make the limit not exist, even though it looks like a smooth curve. Let's see, what are we approaching? X approaches positive 3. Okay, so we're not dealing with a negative right off the bat, right? So that might be okay. Try it. Always try it. Step 1, try plugging it in. Let's just make a little test. What if? Okay, so f of g of x, okay, another way of writing that would be, let's at least get the compound function written out here. We're going to need that anyways. So that would be, start with f. Anytime you see x, replace it with all of g. So we have square root of x, all squared, then subtract 6. Right? In fact, I don't need to make this pink. This is solid, right? We will be using that no matter what. But the pink, I'm going to say, alternate universe, what if We just tried it. Does it break anything? I don't know. Let's see, the square root of 3 squared minus 6. Well, the squaring undoes the square root, so we're just back to 3, right? And then we subtract 6, and then we get 3 minus 6 is negative 3. Oh. Well, this one's actually defined on positive 3. Okay. Let's see if the limit actually agrees there. Because there are some functions, especially when you get to these compound, complex things, you might see a function. I don't remember if this is in tonight's homework or if it's the next homework. You'll see there are some functions that are defined like this. F of x equals, and then you see this large curly brace. Right? You've seen this before. It's like, x squared minus 2 when x is greater than 2, right? But x equals, or not even with x, it'll just say it's just 0 when x is less than or equal to 2, something like that. You seen that before? Piecewise functions, right? They come in different pieces. And usually it's often because something about x being 2 might break things, so they define it. Oh, we got to make it solid for you. They have to fill in the hole that was created up here. There's not actually a hole created in this example, just to be clear. That's what happens when you make things up, all right? That's because without that two pieces together, the limit would not agree. You wouldn't get a continuous function. So we plugged it in, and we found we can fill in the hole with a negative 3. But does the rest of the function actually approach negative 3? Or is this an exception? Is 3 happen to be a unique value to this function? That happens. Again, it's when stuff gets weird. It's a weird case. They're like, you wouldn't expect all these other numbers to do something completely different, but 3 is the magic one, it pumps in. And that's where you see those things that pop up on Facebook, get shared around social media of, oh, I proved that 1 equals 2, math is broken, right? It's because they use some special function where they use the specific case of only if you plug in 1 does this happen. But you're expecting all this other stuff. You expect it still work for any number, but it's unique to 1. Maybe this is unique to 3. That's what we need to test. All right? So we got to approach from the left and the right. Let's take a look. I want to set up a table. I'm not doing that by hand. I know what the compound function now is. I'm going to put that in Desmos and use the table button there. With me? Yeah. Okay, so square root of x all squared minus 6. Let's go here. New function, we want square root of x squared minus 6. Okay, we still have all those negative numbers from last time. It's undefined because squaring the square root forces everything is only allowed to be positive. And we want the limit approaching positive 3 now, right? There's 3. How about a little more than 3? 3.01. 3.1. 2.99. 2.9. So we get negative 3 when we plug in our value, and we get close to 3, negative 3, from either side, right? It is approaching on the left side and the right side. Both of them, we can see our dots there on Desmos. So it agrees. There is no actual discontinuity. The graph is totally continuous around 3. That whole region goes together. No problems detected. This is a good thing, right? This is like when you take your car into the shop, right, to get the oil changed, and they come back and say, oh, right, the 13-point courtesy inspection that everybody seems to include. Hey, we checked your wipers, they're doing okay. We checked your tire pressure, it's doing okay. Right? We checked the other fluids, right? They're doing okay. We checked all the other fluids, they're doing okay. This is a good result. Typically, it's what we want. We want it to be continuous. So nothing happened that's great news. Do not stress about it. Be like, I don't understand. We did this thing and nothing seemed to happen. Good, right? Safety check. Everything's normal. Nothing's broken. All right, so we verified, yes, the limit as x approaches 3 of f of g of x is also negative 3. Okay, final questions. Nothing? Got it? Good, Fernando? Been awfully quiet today. All right. Okay, then you have your homework problems. Go ahead and start taking a look at those. Get some practice in. That'll do it here.